Thank you very much. Good afternoon and good evening to you all. This is the starting point for us is looking at the functionality or the interrelationship, if you will, between water and oxygen in the soil. So if anyone would ask you what is or what are soil physics, or what is soil physics as a scientific discipline about, the simple answer is it's about the balance between water and oxygen in the soil. And typically we're working with courses now where it is, we're irrigated. And as a consequence, the superintendent or the field manager has control over the water and the moisture content in the soil. The superintendent has control over soil fertility because we're actually adding it. What the superintendent does not have control over is the oxygenation of the soil. But there are things that we can do that will give us some control. And for instance, this is one of the reasons why we would aerify. Now, I'm running the seminar both in English on one computer and also in Spanish so that I can see what you're seeing on it, and yet I haven't been able to do my own interpretation yet. I'm sorry, I'm not that functional in Spanish or Portuguese. But
don't worry.
But in any event, on this one here, the basic starting point, as we see, is knowledge without an understanding and interpretation and implementation. So we need to understand, we need to be able to interpret the feedback that we have, what we're seeing in the field properly. We need to be able to implement it, and unless we can do that, it's like, what good is it? It's of no value to us. So we go into the properties themselves. What are physical properties? Well, physical properties are, first of all, physical. They are chemical and biological. So we're familiar with the chemical properties. I mean, that's why we put down our fertilizers, our nitrogen. We have our phosphorus, our potassium. We look at our secondaries and whatnot. The biological is the one that we oftentimes overlook. So with that, we have here the most important one is the first piece of the jigsaw puzzle. I mean, we already had in this one here, we have knowledge. All right, well, that's great. But the plant is everything. So from the biology of the plant, it's like, okay, why do we apply nitrogen to the soil? We apply nitrogen to the soil because the plant has to have nitrogen as part of photosynthesis. So how does that work? Well, photosynthesis, we have the chlorophyll. The magic of the chlorophyll, we are capturing the energy from the sun, from the photons from the sun. We're using the nitrogen and the potassium, and to some extent a little of the phosphorus. And we're capturing that energy and we're converting it into sugars like glucose and sucrose. And so in part of the process, we're taking in carbon dioxide from the atmosphere, and we're taking in water from the atmosphere. And we're breaking the water apart into the 2 hydrogen and the one oxygen component. And then we're creating these sugars. And now what is our byproduct? Well, the plant is going to be exhaling oxygen and then water. But the water that it is exhaling is not the same water that it took in. It has now taken in new oxygen atom and new hydrogen atoms and reconstituted them into a new water molecule. So what is being expelled by the plant through its stomata is actually what you would call new water. All right, fine. So that's great. The plant's got the food, and it's gone through this whole process. And if that is all that the plant does, then the plant dies. And it dies because it had the whole purpose for creating those sugars, capturing that energy from the sun, is so they can take that sugar and distribute it to each one of the cells in the roots, in the crown, wherever, all through the plant. And at the cellular level, then that energy is broken down, that sugar rather, is broken down into its energy. And this is through a process called the ADP and ATP cycle. And it uses phosphorus in it. And in order to do that, then what it has to do, it has to take oxygen into the plant because it's oxidizing these sugars in order to convert them to energy. And what is the byproduct from that? Byproduct is, it's the same process for you and me at each one of our cells. Is we exhale carbon dioxide and water vapor, and the plant does the same thing. Now the good news for all of us is that the plant does not have to use all of the sugar that it's creating, and so it stores it in the roots. And if we want to have a healthy plant, we cannot rely solely on the leaves to take in oxygen for this life-giving process, the oxidation and the conversion of energy of the simple sugars. And so we have that as part of the process as we're storing it there. We also have to think in terms of, okay, so I can't my roots cannot rely on my leaf tissue to take in oxygen and distribute it to me. So as a root, I have to be able to take in oxygen from the soil itself. And this is why we want to oxygenate a soil. One of the reasons, if you think about it, our row crop farmers would till the land is because they want to break up the compaction. They want to allow water to penetrate past a hard surface deeper into the soil. And they want to be able to oxygenate, or what we call aerate, the soil. Well, what we have to do as grass farmers, we don't have the luxury of plowing under our fairways, our tees, and our greens every year. So we have to have a soil that is somewhat conducive to breathing on its own, and that's why we make the move toward the sand. But in any event, this is what the plant needs, is why we have to do what we do. Now, we go on in filling it up, the soil itself. What is the structure of the soil? If we are working with the native soil that has a fairly high silt and clay content, it's going to end up typically being rather hard and very tight. And so that puts more emphasis on us being able to go in there with our tines and our aerification type of equipment, or our slicers, and breaking it up so that we can provide space. And it also is a soil that is going to keep the oxygen near the surface, and so we'll typically have shallow roots simply because of the density of the soil. Next thing we have is sunlight. When you, as a superintendent, are evaluating your greens, one of the things that I recommend is that you keep a little diary or a booklet on each of the greens. And what you want to do is you want to evaluate the microclimate of that green, as well as problem areas and things of that nature. So the microclimate itself starts out first and foremost is how much direct sunlight is my green receiving. I may have areas that have shade. Typically, those have a little bit more stress than others, but here's your starting point, your direct sunlight. We can do an awful lot of things physically to manipulate the soil to adjust for air movement. But if we don't have a requisite amount of sunlight, we can't grow a healthy grass. So that's a starting point. We've got to make sure we have an adequate supply of sunlight reaching the turf. Then the next thing is it's the water. What is our water quality like? You know, do we have problems? One of the research work that we're doing right now is on water quality and how that is locking up soils and destroying the physical properties of the soil. How deep is my water getting? If you are in a position where you're able to use moisture meters, one of the things that I recommend is that ideally we would like to use a 10 to 15 millimeter moisture meter, and maybe even a 20. A 20 would be ideal. A 20 millimeter moisture meter would be ideal to complement with, say, like a 10 millimeter, because the 20 will tell us if we're getting our water down deep enough. And then the next thing we have is the air. Now, when we're looking at the air, we're looking at it from a number of different things. First of all, surface airflow. The surface airflow cools the plant. If I have a surface that is receiving very, very good surface airflows, and by that I mean it's like if you went out there to one of your greens and you would lay your hand flat on the surface and you could feel the breeze on the back of your hand, then you know that you have the surface airflow. Because it's like you're out working on a hot day and you're perspiring and your shirt is wet, and then a breeze comes along, and how does that feel? It says, oh my, that feels great, that is so nice, that's so cool. The same thing happens to the grass. I mean, we could have, we could have the surface temperature of the grass, the surface temperature can be as much as 10 degrees Fahrenheit, 3 degrees Celsius cooler than the ambient temperature. And if I don't have it, if I don't have that surface airflow, the way that what happens is that I end up having an oven effect at the surface. My surface temperature can be up to 20 degrees Fahrenheit. What would that be? 5 to 7 degrees Celsius, hotter than the ambient temperature. With many of our grasses, that can make a big difference between that grass plant being open, having the stomata open and respiring and photosynthesis working and being an active, healthy grass plant, or one that stops down and it goes strictly into maintenance mode. Then we go into nutrients. You're in charge of the nutrients. Plant protectants. These are things that a healthy plant will actually exude many times to protect itself from disease and from pests. That you can also get some protectants from a beneficial bacteria and things of that nature that are living in the soil. And in order to have beneficial bacteria and fungi, we need to have an oxygenated soil, because they are in competition with our roots for the free O2 that's in the soil. And then lastly, the soil amendments, organic matter and things of that nature. Let's go on to the soil structure itself. We have solids and we have pores. All right, and these all dictate to some extent how water and air are going to function within the soil. Larger particles make, we have the large spaces here, and this is what we typically would call air pores. Sometimes you'll see the term non-capillary pores. All right, the smaller spaces down in here, for instance, these are what we call water pores, or capillary pores. These hold water, all right? Water actually drains through the larger pores. It does not drain through the smaller pores. And the larger pores also are the spaces where we will see our root growth. They are also the space where free oxygen can reside within our soil. Within the smaller pores themselves, those hold water. Some that are extremely small will hold it so tightly that the water molecules that are in them will not be available to the plant because the adhesive properties of the water are so strong that the root hairs cannot draw them out of that space. So there will always be an element within any soil, whether it be sand or a native soil, where that water is not plant available. And it's some extent you could say, okay, so what? Because by the time Bob is going to get down to that point, I'm going to have turned on my sprinklers, or I'm going to have my staff out there with the hose watering my greens anyway. So it's like I really don't care. And trust me, I understand that. Because it is true. We don't get down that far. We are typically turning on the irrigation system before then. Now, here we have, in this one here, we have the roots. We're showing the roots now entering into the larger spaces, and this is what our plant is, and it'll start producing other plant matter. Our thatch will start forming across the top as the plant starts maturing and whatnot. And so we see the roots themselves starting to fill the pore spaces. And then the next thing that we have is we now have the organic matter, because one of the things that happens is as the roots grow, they also then die back and then they regenerate, and the residual that's left behind on that process is organic matter. All right, and so that's shown here in the green. And you can see how it goes because the roots are generally growing in the larger spaces. They start getting in and they start clogging up the water pores. So what we'll typically see as a green matures is just, if nothing else, we're going to start seeing that the infiltration rate will start slowing down, so the water movement into and through the soil will slow, and that also means is that air penetration, oxygen penetration in the soil is going to slow and become shallower. And it's also going to mean that the gases that are produced by the other organisms that are living in the soil, primarily carbon dioxide, but other things, will not be voided through the surface as quickly, and so they're going to tend to stay in the soil, and they can start creating a toxic environment, which is not something that our roots want to live in. Now we go on to, as we go through the further maturation of the soil, we start seeing water repellency. Now the water repellency is actually generated by a combination of different things, and one of which is the roots themselves are protected by a waxy cuticle, and that prevents the salts in the soil, the osmotic pressure, from drawing the water out of the roots and having them desiccate. So it's a protective coating, and that sloughs off and is regenerated. So that's one source of repellency, because, as you know, just like any wax that you see, I mean, it repels water. The other thing is too is that the organic matter that's produced by the plant, once it starts drying out, that turns hydrophobic. So that hydrophobic organic matter also repels water. And then we can also have detritus and other dead plant matter, leaves and things. You see that across the top here. That'll start breaking down, and that'll start drying out. And so this stuff can literally repel water. And you'll see it in your greens. I mean, you see where it kind of beads up, you know. And sometimes it beads up right at the surface before we start getting enough water on it to where we can actually start pushing it through. Very common occurrence. And then as we go further through the process, then we have the carbonates. Remember, we were talking about water quality as an issue, and the research that we're doing now on the contaminants in the water as to how they start locking up soils. Well, a major contributor to that are your carbonates. They can be in carbonate form within your water. More likely than not, they're going to be in bicarbonate form in your water. So your most prevalent bicarbonate is going to be calcium bicarbonate. Once it gets in the soil, it'll start going through a chemical reaction and turning it into a carbonate. And so your most prevalent carbonate is going to be calcium, CaCO3, calcium carbonate. Well, in an impure state, we call calcium carbonate limestone. And when we purify calcium carbonate, we call it cement. And when we add an aggregate to it, such as sand or gravel, we call it concrete. And indeed, that's exactly what goes on as the carbonates, which are represented by these kind of blue little dot type things right here, as they increase within the soil, it can actually cement the soil so tightly that it turns into a sandstone, limestone, and sometimes even harder type of a soil than that. So it could actually end up being almost as hard as almost concrete, as a light concrete. And it's all because of the carbonates themselves doing this cementation type of process. And there are ways that we can treat it. And then the other thing as we go through it is then we have sodium. So sodium is very common in our water. I mean, we'll often see in our water reports themselves where we got sodium, and we'll have bicarbonates. So, for instance, if we're in northern Mexico, or say like Arizona in the United States, you know, the arid Southwest, very common for 1,500 parts per million of sodium and 1,500 parts per million bicarbonates in the water. And so what does sodium do? Sodium starts destroying soil tilth. It breaks apart clay particles into their individual little units. It breaks apart organic matter into its own individual little units. And so now these things can start moving with the water and start cementing off and closing off the air pores. It also holds water. And in conjunction with other salts, you could actually have a soil that is so wet, but because it's so high in sodium and salts, that water that is right next to that root, the root cannot take it into its tissue because of the osmotic pressure caused by the salts, and the plant literally dies of desiccation. It dries out because it cannot get the water because of the sodium and salts in the soil. So these are the things then that destroy texture, that destroy soil tilth. And one of the things that we're looking at then is being able to basically reconfigure the tilth of the soil, re-energize it, if you will, or rebalance the water and the air pores through both mechanical means, using various forms of aerification. And then also we're starting to get products coming online that we can use then to neutralize the carbonates, that can help us mobilize the sodium and the salts. And the one thing that's not in here that we're seeing also that's being a contributing factor is our good friend iron. So we've already introduced the salts on it on this one here, and we've already talked about that. Let's go on then. So the book ideally says, in terms of the balance that we should have in the soil of mineral particles versus pore space, it typically would tell us 50% solids and 50% pores. And of that space, it would be pretty much an even distribution of 25% water pores and 25% of the larger air pores. In reality, we really don't get that. Okay, in the real world, what we typically will see is more like 55% solids and 45% pore space. And of that, when we have a new sand-based root zone, very common for it to be like 30% air pores and 15% water pores. Now, as we move along in the green ages and matures, and what causes it to mature is actually the grass itself and all that organic matter that is, excuse me, the organic matter that it is depositing into it, as well as whatever may be being deposited into through the water. So in 2 to 3 years, what we'll typically see would be 60% solids and 40% pores. And now we start seeing them flip to where the things that have been being added to the soil and have been starting to contaminate the air pores have shut down the air pores. Now we're down to 15% usable air pores, and we now have 25% water pores. And some of where we're lost gone from like 50% to 60% of the solids, we also have compaction coming into play as well. So in the real world, what we would like to have is we'd like to have 20/20. And this is where we have to start working for it. Now, our maintainable goals, we're looking at 20% air pores. That's what we want to get to. 15%. If you have greens that are out in the open that have all day sun and have very, very good surface airflow, 15%, you'll be able to grow good grass with that. But as you start getting a little bit more shade, and you start getting, say, a little, some problems with your air movement, you want to go to 20%. One of the things, remember, let's go back to keeping our diary. We recommended doing an analysis of green's access to direct sunlight and also surface airflow. But there can be differences within the green itself between shade, sunlight, and also airflow. So for instance, let's say you have some mounding that is on the windward side, the side of the green where the wind is typically coming from. And this can often be, say like a bumper that flashes up, and you'll typically have a lip, and the wind will come up over that bunker, and it'll come back to the surface some distance from that lip. Rule of thumb: 3 times the height of the impediment is the distance from the impediment that it takes for the air to come back to the surface. So many times what you'll find is that the green that is around that lip or that mounding, that surface area may be stressed, and you wonder yourself, why is that surface area stressed? Well, it's stressed because it's not receiving the same amount of airflow like the rest of the green further down from it. All right. Anyway, so in those situations, we'd like to be able to get more toward the 20% because that helps that soil to be able to counter the negative aspects of that wind flying over the top of it. Infiltration rate. what we would like to see. 150 to 200 millimeters an hour. Yeah, that would be nice. I would say the 200 millimeters is about the minimum that you would like. Okay, that to me is pretty much a threshold. Can we do it with 6? Yes, if you have very good, if it's wide open and it's got good sunlight and it's got very good surface airflow, the 150 millimeters would be sufficient. Organic content, 1.5% to 2.5%. This would be in say in the top. Oh gosh, we break it down by inches. So, and we do it in 4-inch lifts, so the 30-centimeter lift. So so about 2.5 in the top 10 millimeters, and then we would drop it down to no more than 2% in the 10 to 20 millimeter and the 20 to 30 millimeter depth, and then we would probably drop it down to 1.5% on the 20 millimeter to 30 millimeter depths. Okay, so that's how we would look at that, and that kind of gives you an idea, because one of the things is that the organic matter itself, like I was saying before, will start pulling apart, and at the surface, aside from just say sodium causing it to deflocculate, the other thing that causes it to deflocculate is mechanical action, which is caused simply by foot traffic and maintenance traffic. So that's one of the things that, once it starts deflocculating, then that traffic will compress it more tightly, and we can actually seal off our surface. Now, so balanced physical properties, what they do for us is they allow for a more efficient use of water and chemicals. And the reason why is because in the process, in order for our chemicals to be used efficiently by the plant, first and foremost, it needs to be a healthy plant. So it has to have a healthy source of oxygen in the soil that is available to its roots. Second of all, it needs to have a healthy microbial population. Fungi break down the thatch and the root mat of our grass plants. So they are our first step in terms of breaking down the organic matter. Then once the fungi has done its thing, then the bacteria comes in and they break it down further. Both types of microbial populations have to have oxygen available in the soil in order to be able to break down the organic matter, because the organic matter is their food, and they need the oxygen in order for them to eat their food. So one of the things that they do is, as the bacteria in particular consumes the oxygen, breakdowns the food in the form of the organic matter, there is in the organic matter itself things like nitrogen and like sulfur and sodium, not sodium, excuse me, your secondary nutrients and your tertiary ones that we need for respiration, and they put these nutrients now into compounds that now the roots can take up. And so if we have a healthy root system in there, because we have an oxygenated soil, and we also have a healthy vibrant microbial population, now all of a sudden we're breaking down this organic matter, we're using it. We're using it as a positive and as a source of nutrients to help supplement what you are otherwise adding to the soil through your own applications. The other thing is that these bacteria in particular help deliver nutrients to the roots. And the oxygen itself is also necessary for our plant to be able to utilize those nutrients on the cellular level. All right, so now our research has found that the major cause of greens failure is the lack of oxygen. And more times than not, it is caused by too much organic matter in the top 1 to 2 inches of the root zone. And that's what we're going to explore for you and start showing you what this looks like. Okay? So here's one. This green here was established by seed. This core sample was taken about the end of its first year, and it was pretty well, the infiltration rate on it was almost 0. And that organic layer that is highlighted by the arrows was what was impinging the flow of water from the surface into and through the soil. And so here we have that the organic matter itself is the helper, but when we start compressing it into a layer like this, it is of no value to us and can be a liability. So one of the things that we're going to want to be looking through on this seminar, how can I maybe start getting that more evenly distributed so that I can make use of it and utilize what's tied up in it. And use that as a nutritional source in addition to my fertilization program. So here on this one, this slide is included to show you one of the properties that is endemic in almost all organic matter, and that is the swelling. This is what one of our undisturbed core samples look like when they're received in the lab. And at the time they were received, here at the surface, that was flat. Then part of the testing process, they go into a bath and they are saturated for about a day to allow them to get back to their in-field condition. And in this particular situation, what happened is on all of these, the organic matter swelled. And that's what you're seeing here, and it makes it a very nice demonstration because indeed, this is exactly what goes on in your soils. I'll give you an example that you probably experienced yourself. You're out there, and let's say that you're syringing the greens, you're watering them with a hose. Why are you doing that? Well, if I turn on the overhead sprinklers, I put down too much water, and what happens is that my surface becomes too soft and too mushy. That's a function of organic matter. That's also, a property of the fact that it swells. It swells, it gets higher, so it gets mushy, it gets soft, and as a consequence, what you're doing is I'm compelled to only put down enough water to take care of my plant, no more than enough water, because otherwise I'm going to be damaging my playing conditions. I'm going to slow down ball roll. I'm going to, like I say, be mushy, be soft, and increase plugging. And that's not what I want to do, and my golfers don't want that. So this is what causes it. This is a normal part of organic matter. It is, and when it dries out, it is hard as a rock. And remember, when it dries out, it also repels water and it resists resaturation. So, balancing physical properties through aeration. This is where we're going to. All right. How do I do this? How do I use, how can, aside from the biology of the soil, because compaction in organic matter and things like carbonates that are being deposited by my water are going to be locking up my soil. How do I change that? How do I reinsert or insert air pores into the soil in a meaningful way to where it can breathe and water can move again? Well, we do this through aerification primarily. So we typically are looking at 7 questions. 1, how often should I aerify? 2, how deep do I need to aerify? 3, what size tine should I use? 4, what is the spacing between the tines? 5, should I use hollow tines or solid tines? 6, should I fill the holes or should I leave them open? And 7, if I fill the holes, what should I fill them with? And I'm going to back up just a second. I don't want to leave that quite yet to this next slide. How often should I aerify? When I first started in this business back in 1994, and Dave Doherty and I, we brought to the market the undisturbed core testing and got patents on the process. Everything that we saw was brand new to us. And at that time, the standard aerification equipment, we would use 5/8 outside diameter tines, excuse me, what that would be, what in terms of millimeters is probably, I don't know, you can, Xavier's going to have to do the conversion for me on that. But, and it would be on about, 50 millimeters by 50 millimeters, 2 inch by 2 inch on center spacing. So it'd be, essentially 50 millimeters by 50 millimeters on center. And so you go, well, we need to do that 4 times. And that's not practical. But that's how many times they need to do it. And then it was, how deep do we need to go? Well, this is what the core testing was showing. Well, for the most part, if we can take care of the top 3 to 4 inches right now, we're going to be happy with that. So we won't worry about it too much yet. And then, but the problem is that, excuse me, the problem is that we could not handle enough area. So what we started talking about in the reports was displacement. And a superintendent down in Florida, what he did is he wanted to take a smaller tine and actually put it on tighter spacing so he could actually remove more material and actually affect more surface area. So for instance, if the 5/8 on 2x2 displaces 10.2% of the surface area of your green, a 1/2 inch tine on 1.5 by 1.5 center spacing, this, the first one displaces 7.6%. A 1/2 inch on the 1.5 by 1.5 inch spacing displaces 8.7% of the surface area. And so he took an old Jacobson aerifier and tapped out the quad tine blocks so that he could put a 1/2 inch shank tine in there so he could do exactly that. And now those things are commonplace. You can buy them almost anywhere. But that's how it started, by a superintendent wanting to have to affect more area for each time that he took his aerifier out. Now, when we're looking at our aerification, we don't always have to use a hollow tine and pull a plug when we take an aerifier out and be effective. And that's when we're starting to get onto this next slide. So, remember we were talking about, how do I take this organic matter that is accumulating up here in my top 10 to 15 millimeters, and how can I get it deeper? One of the ways is, this is actually a small solid tine, and this is it flowing with the water while that hole was still open. So that's one way we can do it. Another one would be, this is actually a hydroject hole here, where it's actually, the hydroject actually helps blow the organic matter down deeper into the soil. So that's another way. And so now this is taking Mother Nature's gift, and in this form up here, it is actually a liability, and we're trying to make it a gift again. And so one of the things that we're doing is by getting it down here in this particular sand-based green, as a for instance, by getting the organic matter lower, think about what does that do to our microbial populations. If they have to have this organic matter in order to eat, am I not now putting organic matter deeper down to where my bacteria, my aerobic bacteria, have a reason to be deeper into the soil? And the answer to that is yes. So here we have, again, 3 types of aerification in one example. Here we have a sand-filled hollow tine hole. We've got it going through a needle tine, and then we have it with the hydroject. Now the aerification hole itself will seal off. Now this one here was a blunt tine with it. That's what kind of pushed this down, and it came across and filled the hole. But here's what you want to look at. See how the grass heals over, and it caps your aerification holes, your sand-filled aerification holes, with organic matter. So now this sand right here, the sand itself is of that cavity is no value. But if you would come through with, say, like a slicer or some form of a solid tine, and you would cut through this cap, all of a sudden this aerification hole has been reinvigorated and it's useful again. So that's what we call venting, and that's one of the positive things that venting can do, is reinvigorate old, otherwise capped off sand-filled core aerification holes. Now, in our testing, we measure the physical properties. What happens is that the sample comes into the lab, and it is tested for its physical properties. So that'd be infiltration rate, it would be its air porosity, water porosity, total porosity. And we will take, and we do this in 4-inch lifts. So we're doing this in 30 to 40 millimeter lifts. And so we'll take essentially 3 lifts to take to sample typically a 300, but not 30, but a 12-inch or 300 millimeter root zone. Okay, so after we get done doing that, we put it in the oven. We start drying it down, and at that point we take our time-lapse photos, because water releases at different rates from different properties, and we can start seeing the layering. Okay. After that, then what we'll do is we'll remove the grass and the current thatch layer, and then we will test the top inch for its organic matter and for its particle size, sand, silt, clay, and organic matter. We'll do it for the next inch, and we'll do it for the 3rd inch, and also for the 4th inch. Now in this one here, this is an example again of getting sealed off at the surface. As you can see, we've got too much fines up there. It looks like it's organic matter, but in this instance it is not. It is more clay with some organic matter that has been interspersed in it. This was a classic example of the misuse of a very fine compost product. And what the superintendent had wanted Milorganite spread on his greens to help with the grass on. It was seeded with its establishment, and his assistant felt, well, if a little bit's a good thing, then a lot is a really good thing. And in this situation, a lot is not a really good thing. And what happened was he sealed it off, and the grass just could not take. And it was a very difficult establishment process. And the reason why is because it was so tight and so sealed off that the grass could only root up in here where traffic and heat stressed it out. Now, one thing as we're going through here, if you have questions, please ask them as we're going along. If we're having difficulty in the translation or you don't understand something, please ask the question, because you're probably not the only one that is having a difficulty with the translation on it.
Okay, thank you, Bob. Let me tell to the attendees that if they have any question, they can do right now with you. So while you are doing the presentation, they can do the questions. I forgot to tell them before. That's all. Thank you. Thank you.
Well, and here's another example. The roots in the unfilled area. Again, let's bring us back full circle to what we're trying to talk about in terms of the introduction of oxygen. Why do we have roots? That this would be, this was an opened solid tine aerification hole, and it was filled with roots up and down this area. Why would the roots be there? For three reasons. One, you have space for the root to develop. Okay. Two, you've got water penetrating down there, so that's a good thing. Three, there's oxygen in that soil, so it's a healthy environment for the root. Fourth, think about this: the bacteria now, because it also has access to a good source of oxygen, is now decomposing the organic matter, and so those roots in that hole are getting more nitrogen than anything else around that hole. So typically, think about it: when you aerify a green, punch a hole, for however you do it, do you not see the grass around those slits green up? And the answer is yes. That's why, because it's healthier, and it is getting it's getting fed more than the grass plants that are not around that hole or slit. So these are the things that are happening with us, and this is another example of the positive effects of the oxygenation of the soil itself. When is deep tining necessary? Wiedemann's, for instance, are an excellent machine and are typically used for deep tine aerification. When do I need it? Well, I typically need it when I want to start breaking up the soil down below and being able to get the water to be able to flow past the surface area. In this situation here, this was actually a video, okay, and of just taking a hand drill with a very, very long bit and going down through an extremely hard pan area within the soil itself. And with it, what they did is, this is actually a board here, and they did a template of holes so that they could put the bit through there, and as they pull it out, then you have the soil that's being pulled up by the drill right there, and you see the handle here, so you can pick this up and dump it off to the side, and then if you want, you can bring back and put sand across the top of this and very easily fill in the holes. But this is what we were trying to get rid of. This was, hard clay, just locked up, a lot of chemistry going on down below, and what was going on is that on the surface of the green here is that because the water couldn't get down and the soil was saturated, the microbes had gone anaerobic, and when they go anaerobic, they start producing things like methane and hydrogen sulfide, and these things poison our grass. And so by going deep and getting that water deeper and going through this stuff, he was able to get the water away so that his grass could breathe again. Now, many of you are going to have a soil-based greens, and you may be top dressing some with sand, but you're actually, just pretty much working with the soil and how can I maintain a healthy grass within this soil, and here we have what it looks like in terms of the compaction in a heavy organic soil. Now, that compaction that we were looking at before, all right, is primarily just from our golfers. So here's an example of just a foursome. This is the first foursome that went out in the morning, and they were followed, and every one of their footprints was put down, and you can see how they came in, and they all congregated around the pin because they're finishing out their putts and whatnot. And then the calculation was done as to how much compaction was being applied to the surface of that green. Well, it would have been the equivalent of an old brontosaurus or a World War II Sherman tank. And indeed, that's, and that's what you're fighting with it. So one of the things is that what we try and do with it is we try and start taking our soil and modifying it with sand, because sand, even though it's compressed by something like a brontosaurus or a tank or a bunch of golfers, will, if it's properly sized, will resist the compaction. And what we mean by that, it'll be able to have a reasonable balance of water and oxygen in it, and so space for root growth. So that's one of the reasons. So if you're looking at this, let's bring this back to something that's practical for you. If you can, one of the things that you definitely want to do is top dress your greens on a regular basis. The top dressing need not be heavy. In fact, it's better if you could do it light and frequently. So for instance, just a very light dusting. A dusting would be the equivalent of after you get done with the top dressing, you just barely see the sand. That would be a dusting. If you have a verticutter, it's very helpful to, before you do the dusting, go across with the verticutter. The verticutter, its purpose is not to dig out thatch or anything of that nature. On the contrary, what you're trying to do is stand up the grass and also create some space so that the sand that you're applying to the top dressing process is able to work itself down through the crowns. The benefits that you get from this are multiple. One, that's a great way to start changing the composition of the soil on your sand green. Two, it creates a consistent putting surface. Three, it creates a firm putting surface. And so this is probably the most important thing during the playing season that you can do in order to provide a firm and consistent surface for your golfing members. Then likewise, it's like, all right, so fine, Bob, I'm doing that. Is it helpful to me to core aerify my native soil? And that's a little bit more problematic. The answer is yes, if. So it's always the if. If you can remove the plugs, then it is of an advantage to you to core aerify your native soil greens. The reason why you have to remove the plugs is because if you leave them on the surface, then come across with the sand and drag the sand into the soil, what you're doing is you're also going to be breaking up those plugs. You're going to be mixing the native soil with the sand. And what happens is that the native soil is still going to dominate, and you're going to have gone through all of that effort with almost no benefit whatsoever. So if you're going to pull the plugs, you have to, and then come back with sand and fill the holes with sand, You've got to get rid of the plugs in order to make it effective. Otherwise, you're better off working with the top dressing program and solid tines or slicers to be able to manipulate that soil. Do we have any questions on that aspect?
Not right now, Bob. Just one thing. It's for you. It's 11:06 minutes. So just to let you know that you're on time.
We're in a position right now, Xavier, where we could stop. I've introduced them into the basic biology and the basic soil mechanics. We've started getting into how a green ages and why we would want to core aerify and aerify and just aerify in general. We've been looking at primarily sand greens. I know that not everybody has a sand green on it, but obviously it's easier to see the organic matter in the sand greens than in the soil. But the same issues that we have here in sand-based root zones, we have exactly the same issues in our native soils. And in some cases, I've seen situations where the sand was a poor choice, was a very, very fine sand. And in that instance, you would have been better off, in my opinion, with just a native soil green than with a poorly chosen sand for a sand-based green. So these are things that we have to look at. At this point, I think we're getting a little bit too late for them to get into, say, like a USGA. What is a USGA sand? What are we looking at for that, for a USGA sand? Suffice it to say, whenever they're doing, no matter what, whether they're top dressing, whether they have sand-based greens or they have soil greens, they want to have a sand that is as close to meeting USGA specs as possible, because that size, that specification creates a sand that's going to give you the air pores and the permeability that you need for your mature greens.
Okay, Bob. So if you want, we can do the next. As we talked before the presentation started, we can split this presentation in two parts. So if you want, we can schedule another webinar to late May. That it's the next free date that I have.
We can do that.
Yes. Okay.
Yes.
So for me, it would be great because I think that you're bringing us back to the basics, and that's the key of all the turf management. So if you want, we can do that. We can schedule the second part of your presentation to the next free date that for me is on May. So we can talk later by mail and schedule it.
And I would say to our participants, if there are aspects that you would like to have addressed in the second seminar, please let Xavier know so that I can modify and build it to help meet the needs that you're experiencing in the field.
Okay. Sorry, Bob. There is a question from Antonio, from Pedro Rebelo. He's a superintendent from Portugal. He says, some people support the use of a mix of organic matter and sand to address the new sand-based greens.
Yes, they do. I'd have to know a little bit more about that, Antonio. As a general rule, I would say no. Once your grass has been established, I would use the sand. If it's a good sand, I would use the sand, but I would no longer use the organic matter. Because as you saw in one of the very earliest slides, what organic matter at the surface, how that can be compressed by the foot traffic and start sealing things off. The grass itself, once it's established, is generating its own organic matter. And generally, we do not need to keep adding organic matter to it. Now, the caveat is that if I have a very, very light mix, there are times when it makes sense to use a sand peat or sand organic blend to top dress. But those times, it's been my experience, are very, very rare. And unless there's an extremely good reason to do it, I would just use the sand. One last point. The idea of using the same mix to top dress with was like we're trying to keep a layer from forming. What we have found over the 22 plus years that we've been doing undisturbed core testing is that layering occurs whether you use the same mix or a different sand or the same sand. And the reason why layering exists is because the grass is producing its own thatch and root mat. And as a consequence, when we top dressing, it's staying on top of that root mat and the thatch is being buried. And ergo, it is a layer in its own right. The question becomes is whether or not the sand layer that you are applying through the top dressing is compatible with what's down below. And usually, if you built your greens with a very good quality sand, that will make a very good quality top dressing sand.
Okay, he says that he agrees. Pedro has another question. He said, "What about the same sand of the construction and zeolite? Zeolite, sorry."
First of all, you have to make sure, Pedro, that you're using a very good quality zeolite. There are hundreds, literally hundreds of zeolite sites and mines around the world. And very few of them produce a product that we want to put into our greens. The benefit of using zeolite is that it is very, very high on CEC. So I typically like to use it at about a 5% by volume mix ratio. And I like using it for new construction, so I have a nice homogenized soil with the zeolite within it through the entire green. And so that way I know that I have consistent nutrient retention sites throughout my soil. Now, that said, I've worked with zeolites from pits that are not desirable. One, for instance, was down in southern Texas, and when it came into the lab and I put it in water, and it created a milky white slurry. I got it on my pants, and to this day I still can't get it out of my pants, no matter how much I wash them. You know, whether by hand or a washing machine, makes no difference. It's not coming out. And when I put it into a mix with a very good sand, it just locked it up and was completely unsuitable. So you have to watch the product. Not all zeolites are created equal. But when you find a very good one, it's a very fine product. Now, would I use that to top dress with? No. Would I use it in a mix to fill aerification holes? Probably not. And the reason why is because it is, we're talking about 200 milliequivalents per liter for cation exchange sites. That's very, very high. Typically, you as a superintendent would like to have 6 to 8 milliequivalents per liter in order for you to maintain control over the fertility of your soil. So when we're using it as top dressing, we're going to be holding nutrients at the top. You're going to run a real risk for algae. And if you're putting it into aerification holes, you're running the risk of creating nutrient hotspots in your green where you won't have control. So, but I definitely would use it, and I have no problem and do recommend it for using it for new construction.
Okay, Pedro, appreciates very much your answer. There is another question. What do you think about using hydrogen peroxide to manage organic matter in the topsoil?
I don't have a problem with it. It works. It helps. It's also used to introduce oxygen into an oxygen deficient soil. The problem that you have with it is that you have to spend money for it, and so typically it's cheaper to open up the soil or to remove the organic matter mechanically with hollow tines or with, say, like a deep slicer, like a Sisis or maybe a Planet Air, and start digging it out rather than using the hydrogen peroxide. So from a financial matter, it's good to you can use that, and it's a good tool to use when you need to have relief right now. But for a long-term effect, it's probably too expensive to use.
Okay, perfect. And there is another one. What do you think about the microbial population management? Is it taking more importance in turf management? So what do you think about the management of microbial?
Excuse me. I believe that we need both the mechanical removal and manipulation of the soil in addition to the biological manipulation of the soil. What do I mean by the biological? Think about this. So long as we have an adequate soil temperature, there are three things that dictate the size and the vitality of our microbial populations. That is food, which is the organic matter. Typically, we have more than enough of that. Second one is water. You're in control of water. And the last one is soil oxygen. So if I want to have a healthy, vibrant, aerobic microbial population that is living synergistically with my grass, and my grass is being a benefit to those microbes as well as they're benefiting my grass, then it is necessary for me to do everything that I can to help maintain a well oxygenated soil. And so what that means is that I have to have a soil that has enough permeability so that this carbon dioxide and the other gaseous byproducts that are created by my microbes living in my soil, so that can be released, and excess water can be released, so that then oxygen from the atmosphere can come into the soil, rediffuse, get down deep, and replenish the needs of not only my microbes, but also, remember, my roots, because my roots are in competition with my microbes for that O2. Also remember this: 26% of the atmosphere is oxygen, and 73% of the atmosphere is nitrogen. 1% of the atmosphere is everything else. Carbon dioxide is like 0.06%.
Okay, thank you very much. There are no more questions. I think that your presentation has been very, very, very interesting. So let's do that if you agree. The second part to late of May. We'll talk later to fix the date. So thank you very much again, and that's all. Let me say some words in Spanish to say goodbye to the attendees.
Please.
Okay, Bob. Pues nada, como veis, la presentación de Bob Oppold da para mucho, así que como considero que es muy interesante el tema, pues que haremos una segunda parte hacia finales de mayo. O sea que, bueno, seguiremos hablando. El próximo webinar será el 6 de abril y volveremos a colaborar con la profesora Elizabeth Gertel de Auburn University. O sea que es una gran comunicadora y una especialista en gestión de céspedes a nivel mundial. O sea que tendremos el placer de volverla a tener con nosotros. Ya fue la primera profesora a nivel internacional que tuvimos y es un placer para mí pues volver a colaborar con ella. Entonces, por mi parte nada más, agradecer de nuevo a nuestros patrocinadores que con su ayuda pues vamos ofreciendo estas píldoras de formación. Okay, Bob, so thank you again.
You're welcome.
If you want to say goodbye to the attendees.
I do indeed. Thank you very much, gentlemen, for spending your time with me.
Okay, I'm sure that they have enjoyed a lot with you. Okay, so pues muchas gracias a todos y hasta el día 6 de abril. Okay, Bob, thank you very much. Let's keep talking.
Okay.
Okay, bye-bye.